Yeah, so I'm going to talk, kind of continue on with where we left off yesterday, talking about now planetary dynamos, though really I'm just going to talk a bit more about dynamos in general. Stellar dynamos and planetary dynamos are different in the details, but in the broad strokes, they're actually very similar. But what I thought I'd just kind of start out by asking is, out of curiosity, how many in here know which way the compass needle points right now? Well, sorry, I mean the actual direction. So if you pulled out a compass, do you know where it would point? It's kind of interesting, right? I mean, oh, one person? You can actually point to where the compass. True north versus magnetic north. So the interesting thing about geomagnetism is that people also cared about this long before they had any theory of electromagnetism. This is just a map. That's a nice slide I got from Helical, who's at Princeton now. This is showing the direction that the compass needle would point based on where you are on the Earth. And so you're seeing kind of deviations from true north versus magnetic north. And this was important when you're we're sailing a long time ago when you needed to navigate, right? This was helpful. What's interesting is you can take data like this because people kept very detailed records because it mattered quite a bit. And you can actually look at how the Earth's magnetic field evolved over time. And so when we look at the Earth's magnetic field, we see over very long time scales, maybe not over human time scales or particularly noticeably over human time scales, there's actually quite a bit of evolution in the field, right? It's a dynamic magnetic field. And if you look, you see that it's predominantly dipolar, right? So in this case, we've got the negative polarity coming out through the North Pole and the positive polarity coming out through the South Pole. But there are these blotches, right? And this is what people were recording. There are other components to the magnetic field that are not dipolar at all, right? The other thing you might notice, if you look at this long enough, you'll notice that the field tends to drift in a certain direction. And that's westward, so this is actually just referred to as the westward drift of the magnetic field. As far as the geodynamo goes, this is one of the open questions right now. What causes that drift of the magnetic field? And there's really kind of two leading possibilities as far as I understand it. One is that the field is anchored into a flow, so there's some sort of differential rotation in the Earth's core, and it's just pulling this magnetic field along with it. The other possibility is that this is some sort of a wave phenomenon. It has nothing to do with transport by flow, but it's actually a wave in the magnetic field, or possibly some kind of wave that involves the fluid as well. But the important thing here is, we tend to think of the Earth's magnetic field as somewhat static, but it's not. It's dynamic. So it's not just that we know that there's a dynamo because the field has been sustained against decay. I forget someone put it on their slide. I always forget these numbers. The decay time for the Earth's magnetic field is actually pretty short relative to the age of the Earth. But it's changing with time as well. It's a very, very dynamic magnetic field. The Earth is not alone in the solar system. Most of the planets in the solar system actually have magnetic fields as well. Some of them, such as Mercury and Saturn, are fairly axisymmetric. Others, particularly like Neptune and Uranus, are not. So the fields can be very simple. Saturn, in particular, is a very, very simple, very axisymmetric magnetic field, and that's something of a mystery as to how that comes to be. Or they can be fairly complex. And these measurements are taken from a variety of different spacecraft. And I used to have a slide that labeled them, and I'm not sure where I put it. So, in any event, these are observations. Yes.
So, at least in terms of Earth and other planetary dynamos, there's polarity reversals. How do we know that Uranus and Neptune aren't sort of maybe some sort of polarity reversal?
I don't know how we would know, right? I mean, we have these observations just since the space age, right? And so since I'm not sure when the earliest observations of, say, Uranus's magnetic field were made, but they certainly were not made before 1960, right? And so that's a great question. So for the recording, the question was, how do we know that these fields that we see on, say, Neptune and Uranus are not just indicative of the fact that they're undergoing a reversal, perhaps a very slow reversal? And the answer is we don't. So this is kind of just a quick overview, and we'll talk a little bit more about these different bodies briefly. Where are we going? We're going out into the solar system, but I thought what I would do is sort of pick up a little bit on where we were yesterday and revisit some of these fundamentals of dynamo theory very briefly. But then I wanted to talk a little bit about this notion of rotating convection. We talked about how helicity is central to sustaining a dynamo, helicity of the flow of the conducting fluid, whether that's a plasma or a molten metal. And I'd like to kind of visit this a little bit more, in particularly because, as solar physicists, we have just these beautiful data streams coming from all of these satellites that are observing the sun, 24/7, right? We see magnetic field. It's hard not to focus on the magnetic phenomenon themselves. I also hang out with some of the more planetary dynamo-oriented crowd, and they don't have the same data that we have, and so they actually tend to think quite a bit still about the convection that's driving the dynamo. And so I really want to talk just a bit about convection, in particular its interaction with rotation, and then we'll see some interesting examples of how that manifests in models of planetary dynamos. Once we're kind of through that, we'll actually start talking some about the different bodies in the solar system. And then finally, I'll talk a little bit about models, right? And you can imagine why modeling is even more central to planetary dynamo studies than it is to, say, solar dynamo studies, just because our ability to probe the cores of any planets other than Earth, say, is very limited. And even in Earth, much as with the sun, it's limited in terms of our ability to probe the flows. Okay. So just to kind of review, let's not forget the central thing that we care about here, right, which is the MHD induction equation. And we have, this source of magnetic energy, which is this V cross B term. And then we have this sink of magnetic energy, right? And if we want to see that more explicitly, we can just dot this equation with B. Sorry, there's a little animations here. And we come up with an equation for the magnetic energy and how it evolves with time. And there's a few terms, right? There's a pointing flux, basically just what you have seen in your E&M class, though possibly a little different since we've got V here and we're working in the MHD approximation. There is this ohmic dissipation term, which really just depends on the square of the current density, so that's where most of the dissipation is happening. And then we have this other term, which is kind of interesting, right, which is this work against the Lorentz force. And so this could be either a positive, so a source term, or a sink term, right, depending on the sign of V here. Okay. We know that what we ultimately want, if we want to sustain a dynamo, is for this magnetic Reynolds number, which we denote by Rm, which is just really the ratio of these two terms where we use typical values for the velocities in the length scale. We want this to be much larger than 1, but we do have to be a little careful because the spatial scale here of the magnetic field itself might be very different than the spatial scale of the correlations of V and B. Okay? So greater than 1 is necessary, but not necessarily sufficient to sustain a dynamo. And this ultimately, the sort of dynamo you drive depends quite a bit on the flows and the structure of V. Skip that slide. And One thing we're going to visit in a little bit, which you've seen, is this notion of a diffusion time. And we're going to actually calculate this together, but based on the length scale, say the depth of the Earth's core, the depth of the solar convection zone, and then based on the diffusivity, eta, the magnetic diffusivity, we can actually get a sense of how long it's going to take a magnetic field to decay away if we just plunk a magnetic field in there and let it sit. How long will that take? And for the Earth, it's about 100,000 years. That's nice. I know I had a clue on one of my slides here somewhere. For Jupiter, it's actually quite long, 30 million years. For the Sun, it's kind of fascinating, and for most stars, the magnetic diffusivity is so low for stars in general that a typical decay time is going to be close to the current age of the universe. And so for the Sun, if you had a primordial magnetic field, it's possible that it would still be there even if there were no convection. Okay? And that's a very broad, vague statement, right? Possible. This depends on other things as well. But in the case of the Sun, we know that there is a dynamo because we see the magnetic field changing. In the case of the Earth, we can see the magnetic field changing, so there must be something going on with the dynamo. And also, the decay time for a magnetic field, if it were just left over from the formation of the Earth, is much, much shorter than the present age of the Earth. And so we know that something is going on inside the Earth to sustain a magnetic field. So, in general, right, what are the conditions for sustaining a dynamo? We're going to just revisit some thoughts from yesterday. But first, you need some kind of conducting fluid. And what this is that's really what you need, a conducting fluid. If you're a star, it's a plasma. If you're a solid core of a planet, it's probably something like iron. That's what we think it is in the Earth's core. Some of these ice giants have interesting mixtures of things like methane and ammonia, water. We think some of the icy moons around Jupiter and Saturn may have salt water. And then it's not sufficient to have the fluid. You need to have some kind of fluid motions, right? So the fluid needs to be moving around for some reason. Typically, that's going to be due to convection, right? So if the fluid needs to transport heat, then convection is going to be what constitutes the fluid motion. Okay. And then you need your diffusion to be sufficiently low so that this source term, the V cross B term, can win out over the dissipation. A couple of other things that can help. Rotation. Rotation, as we talked about already, and we're gonna get into this in a bit more detail in a minute, is really good at helping generate helicity when you have convection. It can be bad, though, and interestingly enough, because the Coriolis force can compete with the buoyant rise. It can work to, sorry, it's early morning, I'm still getting my speech back. The Coriolis force can suppress the buoyant rise of warm parcels of fluid. And so you can actually suppress convection if you're rotating too rapidly. And so rotation is kind of a double-edged sword. But in general, it seems to help. Turbulence, similarly, it can be good for stretching magnetic fields on small scales. And then that in tandem with rotation can help you generate organized magnetic fields. The problem, of course, though, is that if you're moving magnetic field around quite a bit on small scales, you are also potentially bringing in field of opposite polarity into close proximity, which will then increase your ohmic dissipation. Okay. But we think that these are pretty much typical ingredients of natural dynamos, at least as far as planets and stars are concerned. Okay. So I wanted to revisit this notion that rotation helps generate helicity. I sort of said this yesterday and then didn't get into it very much. And I wanted to talk a little bit about convection. I'm just kind of curious, how many of you have had a fluids class where you've talked about convection at some basic level? So maybe kind of half of you. And then, so I'd like to talk just a little bit too about what convection is. When we talk about things like the Rayleigh number, what that actually means, the Ekman number, we talked about the Rossby number yesterday. So we'll get into the Rayleigh number in a little bit of detail, and then we'll talk about the Ekman number briefly and review the Rossby number. But convection is really good, or excuse me, rotation is really good at generating helicity both on small scales and large scales when there's convection present, right? We get differential rotation out when we have convection and rotation together, and then we have helical rolls, which is what I really want to talk about today, that arise due to rotation. And so these help to drive a differential rotation, but they actually are helical on much smaller scales than the system scale, or they can be. It depends a bit on something called the Ekman number, which we'll talk about in a bit. And this is just an example from yesterday to give you kind of a sense. Here you're seeing some of these roll-like structures, particularly near the right. So we're moving from a non-rotating model to a rapidly rotating model. And you're just seeing basically the upflow pattern. So red is upflow, it's ascending, and blue is descending downflow. But as you rotate more rapidly, these columnar structures become thinner and thinner. And they're actually thought to be quite thin, and the Earth's so thin, in fact, that they're probably not even columns anymore. And we'll talk about that in just a bit. Okay. Let's move through that. And then there's just kind of another view. So I showed this nice schematic from Peter Olson several years ago, just showing how these columns are helical and how they have this propensity for generating poloidal field from toroidal field, and vice versa. If you have a poloidal field threading one of these things and they're wrapping around in sort of a spiral fashion, it will take the field with it. And so as you wrap that field that was once vertical, you start to get twist in it. Okay. And so what I would say is that this structure, this flow structure, or its more turbulent counterpart, and I'll show you what that might look like near the end of this talk, is what probably forms the central engine of most dynamos. And so I think it's useful to ask, where does this come from? At least get some sense of what's going on. So what I'd like to do is just talk for a minute about convection, and then the role of rotation in helping to generate these roll-like structures. And so I'm going to go through this fairly quickly, but you can revisit these slides, and hopefully I don't have any typos here that will just confuse you later. But the idea here is we'll just start with the momentum equation, and we're not even going to worry about magnetism right now. Okay. As far as the convection is concerned, we'll even see later, you get very similar flow structures. And so we have our advective term, U dot grad U. We have a Coriolis force, a buoyancy term, a pressure term, and a diffusion term. And we're considering an incompressible flow with constant diffusivities and a constant background density with small perturbations about it. Okay. We'll assume that the pressure can vary with radius so that we can actually maintain some sort of hydrostatic balance. And I'll denote perturbations about this background state with little primes, okay? And the idea is that these perturbations are small. In practice, they're something like 1 part in a million. That's kind of the typical estimate for both the Earth and the Sun. And so it's kind of fascinating, actually. If you think about the Sun, so this holds for temperature perturbations as well. If you think about the Sun, the top of the convection zone is about 6,000 Kelvin, and the base of the convection zone is about 2 million Kelvin. The convection is driven by temperature perturbations which are on the order of a few Kelvin. And so it's kind of fascinating to think that everything that, all of this heat transport, transporting the full energy output of the Sun is accomplished with very, very small temperature perturbations. Okay. So all we're going to do is we are going to subtract out the hydrostatic balance, okay, which will give us a balance between rho bar G and the radial gradient of the pressure, the mean pressure. And then we're going to divide by rho bar. And the important thing is that we see now that our gravity term it responds not to the full density, but rather to perturbations about the background density, And so that little prefactor in front of G, we might expect to be something like 10 to the minus 6. Okay, so it's very small, but it's important because that's what drives all the motion. And then the next thing we'll do is we'll recast our the density factor in terms of the temperature. Okay, and so the way that you typically write this when you're working in a Boussinesque or an incompressible system, we just say that relative density perturbation is proportional to temperature with this constant alpha, which we call the coefficient of thermal expansion. Okay, so the idea here is that alpha, whatever it is, it depends on the properties of the fluid. It's larger than 0, so that if we're hotter than our surroundings, we get a negative density perturbation, right? So if something's hot, it's a lower density. And then if we're cooler than our surroundings, we get a positive density perturbation. Okay. So we recast the equation here, and now I've written G with a radial vector there instead of a bold G. And we see, okay, so what we kind of already knew intuitively, or we learned in high school, right? Hot fluid rises and cool fluid sinks. Okay. And provided that the buoyant driving is greater than the viscous dissipation or the thermal dissipation, we can actually get convection. Okay. Right. So when we're working with planetary interiors, the way these are typically modeled, and it's not a terrible model, particularly for the Earth, is that you have kind of two boundaries, a lower boundary and an upper boundary, and one is held at a constant hot temperature and the other is held at a constant cool temperature. Okay, so much of the geodynamo modeling is actually done just like the kind of canonical Rayleigh-Benard problem. And the idea is that because we have a temperature gradient, conduction is able to pull energy in through the inner boundary and extrude energy out through the outer boundary. Okay. And in the absence of convection, if we were just in a plane layer, we would just have a linear profile for temperature. In a sphere, it's a little different. You get some geometric factors just due to the fact that your inner sphere is, smaller than your outer sphere by a factor of 1 over r squared, or r squared. Okay. And all we want to do is we just want to consider a little warm parcel of fluid and a cool parcel of fluid. Okay, so a warm one near the bottom, a cool one near the top, and we just want to perturb the system just a little bit. Okay, so we're just going to displace those ever so slightly. But what's happened once we've displaced those? Well, initially, our parcel of fluid was at the same temperature as the background, right? Okay. But since we've displaced them, we have a temperature perturbation now. And so the warm parcel is it's still the same temperature, say, but it's warmer than its background. And the cool parcel, if its temperature hasn't changed significantly, is now cooler than the background flow. And of course, what's going to fight against this, right? What's going to try to keep these parcels from not having any perturbation relative to the background? What do we think? Thoughts? So if the temperature diffusion is sufficiently high, right, these things will eventually equilibrate with the fluid around them. They'll lose their heat or gain heat, depending on which parcel we're considering. But anyway, if that's not happening, then the one on top will continue to rise and the one on the bottom will continue to fall. Okay? And so what happens is that over time, this process will modify the background temperature profile. Okay? So we might, depending on how efficient the convection is, we may just make a small perturbation, kind of like the middle curve there. Okay, so we're no longer a straight line, we're just curved a little bit. But if we have very efficient convection, what happens is that it will work to wipe out any gradients in temperature over some region of the domain. Okay, so that's kind of the order 1 effect of convection, is to modify the temperature gradient, or really the entropy gradient, and to make it as flat as possible over as wide a region of the domain as it can. Okay. But the question is, what determines whether or not you get from the weak state to the strong state, or which state you get to, starting from your conductive state. And so to answer that, we have to think a little bit about the internal energy equation. So if we're working with an incompressible gas, constant diffusivities, this is what the internal energy equation looks like. There probably should be a CP factor there. What would factor out? So yes, there shouldn't even be that. Okay. So it's just an equation for the temperature of the fluid. And we have two terms. We have advection, so movement of the fluid by the flow. And then we have a diffusion term. Right? And so these things are in constant competition with one another. Right? And so what happens is that as the fluid parcel rises, it's going to start to diffuse. Okay? So it wants to mix with its environment, and this mixing happens both in terms of the temperature of the parcel. It's trying to come into temperature equilibrium, but it's moving through a fluid that has viscosity, and so it's also mixing momentum. Okay, and that's kind of important. Both of these effects are important. So it's mixing as it goes, possibly entraining other fluid. So this is kind of the basic idea here. So there's this constant competition between the buoyant driving and the diffusion of the momentum and the heat. And the question is, which one wins? And you can actually quantify that through this number known as the Rayleigh number. And so, a little surprise here. I know it's early, but let's all kind of put on our thinking caps for a couple of minutes and do something on paper. Okay? You can probably almost do this in your head. But let's just consider a very simple 1D diffusion equation. So we just take advection out of here altogether. And let's just try to search for a solution of this form. Okay? So we've got an exponential and a sinusoid. So an exponential in time and a sinusoid in space, right? What do we come out with for this number tau? And I'll give everybody, it is early, so I'll give you 3 minutes. So I've got a little timer here. So take just a minute, kind of get your mind in the game. And then we'll see if I have the right answer. There's a big storm last night, at least in Broomfield, so I've actually been awake since 3 in the morning. So I did some revisions around 4:30. So I don't know if that was wise or not, but so we'll give everybody just a minute. Have a sip of coffee. You've just been getting the fire hose of talking, and now suddenly, hey, to use a pencil. One more minute. What's that? Do you know what? I can see my slide in preview view. I also did on the slide. The true answer is we can never know. Okay, so hopefully you all found that tau has this form. There should be a minus sign there as far as actually plugging that into the differential equation, which tells us that this equation describes the decay of something, right? So that's the ultimate role of diffusion, is to help the heat decay away, at least locally. It depends, of course, on the gradients and on the form of the function that is being diffused, but that's sort of the primary role. I see some confused looks. Have I made a egregious math error? Oh, the pi squared should be in the bottom? I'm sorry about that. Yes. Excuse me. Yes. So this is the 430 mathematics here. So in any event, we're going to neglect the factor of pi squared there. Okay? And so what this is giving us is what we would call the characteristic diffusion time for some structure of length scale L, or a diffusion time across some length scale L. Okay? So if you want to know the characteristic diffusion time for the Earth's core, you would plug in the appropriate value of kappa for a liquid iron at a temperature. Oh, interesting fact. Who knows? Curious thing here. Who knows the central temperature of the Earth? It's very close to that. Yes, it's around 5,000, I believe. But good guess. The radius of the Earth is about 1,000 kilometers, which is the characteristic scale. Or excuse me, the radius of the core of the Earth is about 1,000 kilometers, which is the characteristic scale of convection on the surface of the sun, right? The granulation scale. And so there's this interesting connection between the two. In any event, if you want to know the diffusion time for the Earth's core, the solar convection zone, you just, kind of as an approximation, plug in the depth of that layer and then the appropriate value for kappa. Or if you're thinking about momentum, you would plug in the appropriate value for the kinematic viscosity here. Okay? All right. So those are two very important timescales when we're thinking about convection: the thermal diffusion time and the viscous diffusion time, which you could get. They're very similar exercise, just thinking about the momentum equation. But if we want to think about the movement of the fluid, we also need to think about the buoyancy timescale. Okay, so a typical time for some parcel of warm fluid to rise across the domain, or some parcel of cool fluid to sink. So let's do one more little bit of math here. Okay, so I've got very simple differential equation. Okay. We're just considering just the buoyancy term. And we're going to say, hey, we've got some typical temperature that's constant, okay, T twiddle. Okay. What is the free fall time across the domain if it's got a depth of L? Okay. Very, very simple exercise. Right. Here we've got the second derivative of position with respect to time. So we just integrate this thing twice. So what do we get? Let's go through that really quickly. And this will be, I think, the last pencil and paper thing I'll have you do. Everyone will either be awake or annoyed. So this is my force, right? This is my gravitational acceleration, basically. I just drop this thing from a height L. How long does it take to fall? We'll do 90 seconds. All right. So hopefully we all remember first semester physics. Integrate this thing twice, starting from rest, and you should have come out with something like this, right? Square root of 2L over alpha Tg. Okay. So we would call this the buoyancy timescale or the free fall timescale. I hear both depending on who I'm speaking with and which article I'm reading. Free fall is probably what I tend to, it's probably a bit more common. Okay? All right, so what do we do with this? Well, oh, that's funny. A little unfortunate animation there. So now we have these three timescales. If we want to quantify the competition between diffusion and buoyancy, so viscous diffusion and buoyant driving, or thermal diffusion and buoyant driving, what we might do is we might consider the ratio of these different timescales. But since we're considering two different timescales, we might consider them as a product. Okay. And when you do this, if you take the ratio of the thermal diffusion time to the free fall time and the viscous time to the free fall time, what you come out with is what's known as the Rayleigh number. Okay. And the Rayleigh number is what ultimately describes how efficient your convection is, really in tandem with another number called the Ekman number, which I'll mention in a moment. But if you're not rotating, if you're considering just a pot of, well, that's actually not a good example. If you're just considering a fluid between a hot and cold plate and it's not rotating, this tells you pretty much everything that you need to know. Or from this number, you can figure out other things related to the efficiency of the convection, how well it transports heat, how much flux it's going to pull through the system. For a non-rotating fluid, you need a Rayleigh number of about 1,000 in order for convection to kick in. The details will vary, but order 1,000 is what you need in order for convection to start. Okay. So if we looked kind of back at this plot, we might just recast this as sort of small Rayleigh number and high Rayleigh number. Okay. So when we're talking about convection, this is really all we're talking about, and there is this one non-dimensional number which we use to sort of characterize the competition between the stuff that wants to drive convection, the buoyant driving, and the things that want to kill off the convection, the viscous and the thermal diffusion. Okay. So the next question is, we talked about how, okay, the convection then becomes helical when there's rotation involved. And rather than go through a whole bunch of math, I'll just say, hey, why do we have helical rolls? First, I should say, why might it be helical? I'll talk about the roll aspect in a second, so these big columnar structures. But if you were to write down your momentum equation and just stick the Coriolis force on the right-hand side, and compare that, for instance, to what you would get if you plugged in the Lorentz force, right, from sort of second semester physics, you notice that these equations look basically the same, right? The rotation vector, which is always pointed in the one direction, acts just like a magnetic field. Right? So if you have a parcel of fluid trying to move under the influence of a Coriolis force, you can get spiraling around the direction of the rotation vector, just like you would spiraling of a charged particle around a magnetic field line. Okay? Mathematically, this is the same equation, right? I just changed the names of the actors involved here. Okay. So kind of moving forward, so a couple of other important numbers. We talked about the Rossby number yesterday, and we just talked about the Rayleigh number, right? So with the Rayleigh number, we're concerned about dissipation timescales relative to buoyant driving timescales. Then we have this Rossby number, which is telling us something about the importance of the Coriolis force on the fluid flow. Okay, so it's telling us how likely we are to get that spiraling motion. If the Rossby number is very high, it means that the convective timescale is very short. And so a little parcel of fluid will just fire across the domain before the Coriolis force has any time to act on it. Okay? If the Rossby number is low, we have the opposite situation. The parcel tries to move, but the rotation is so rapid that the Coriolis force steers the parcel of fluid around. Okay? And then there's this other number, which is kind of related to these two, which is the Ekman number. And it's just giving us a ratio of a rotational timescale to a viscous timescale. Okay? So it's kind of telling us how much viscous diffusion wants to fight this spiraling motion, for instance. And this is used quite a bit. In the Earth, the Ekman number is very low. I'll show some numbers in a minute. It's actually low in pretty much any natural system that you might care to consider. So what that's telling you is that the role of diffusion relative to the Coriolis term is pretty minimal. Okay? So when we're studying a planetary or a stellar dynamo, we expect diffusion to play a minor role, at least on the microscopic scale. It's possible that we can generate turbulence that then acts like a diffusion on small scales, but the microscopic diffusion for these systems is actually very small. Okay? And in fact, when we're considering planetary dynamos in particular, the role of rotation is quite large. The Coriolis force can play a huge role in the dynamics in planets, and it actually does in a lot of stars too. And yesterday I was saying we don't quite know what the convective amplitudes are deep inside the sun, what the characteristic flow speed of solar convection is deep down. It's possible that rotation is playing a dominant role there as well in the dynamics. But for any planet, certainly, both the Rossby number and the Ekman number are very, very small. So what we know is that rotation dominates convective flows, or just the inertia really, and then it dominates over diffusion as well. So in the case of the Earth, for instance, if you're just trying to get kind of a rough sense of the Rossby number, how frequently does the Earth rotate? Someone tell me. You in the orange shirt. Sorry, I can't see your name tag. How frequently does the Earth rotate? Once a day, thank you. Right? We think that the convective overturning time in the Earth's core is something like 100 years. Okay? And so the ratio of these two timescales is quite disparate, right? So 100 years would be like 10 to the 4 days, right? And so the Rossby number for the Earth is something like 10 to the minus 4, probably like 3 10 to the minus 5 if you account for the 365. Okay. I'm not going to get into this too much. This is a slide I got from Mark Misch, but the important thing here is that when rotation dominates, you get what's known as this Taylor-Proudman effect, which is that flows want to be invariant as possible in the direction parallel to the rotation axis. Okay? And so you might ask them, what does that mean for the convection, right? So you say, well, what would convection look like in a rapidly rotating spherical shell? Okay? So we have two effects going on. Right? We have helicity of the flow due to the Coriolis force, and then we have the fact that buoyant driving is trying to push this stuff out radially, right? And so we're getting this spiraling, and it's sort of sustained by the buoyant rise or the buoyant sinking of cool fluid. But then we also have a flow that wants to not vary along the rotation axis. So you say, well, how can I get the heat out? Somehow the fluid needs to be moving radially outward somewhere. And so it turns out that's in the equatorial plane. And that's how you get these rolls. Okay? And so these rolls are kind of interesting. So they're helical. Busa did a lot of work on this back in the 70s, and he goes into the linear theory and how you get these rolls. There's a few interesting aspects here, though. The first one is that you might imagine that it's not quite clear why we're helical, right? Maybe the fluid just moves around in this direction. Why does it have to do this at all? And the answer is that we're actually breaking Taylor-Proudman at the boundaries, right? This roll can't be invariant in Z everywhere because eventually we hit this curved spherical boundary. And what happens is that the primary balance you get in these sorts of systems is between the Coriolis force and the pressure force. And you end up getting a pressure gradient along these rolls going from the equator to where it intersects the spherical boundary. And that helps to push fluid up or down the roll depending on which way it's going, whether it's rolling in the same sense as the system, or if it's if the rotation vector of the roll is misaligned with the rotation axis, you'll get kind of different pressure gradient senses along the roll there. The other kind of interesting thing here, though, is that when this kicks in, the spatial scale that you get for the roll is actually determined by the Ekman number, and it scales as Ekman to the minus 1/3. Okay? So if you're ever at a Dynamo kind of conference, you'll hear Ekman to the minus 1/3 or Ekman to the 1/3 pop up all the time. Okay? But the idea here is that as the Ekman number becomes lower, notice this is, unfortunately, this is wave number, right? So as the Ekman number becomes lower, the wave number of these rolls becomes higher, which means they are becoming thinner. Okay? So the lower your Ekman number, the thinner the roll-like structure that you might expect to get. And I'll just kind of briefly mention the rolls, depending on the geometry of your convective layer. You can ask, where can I most efficiently generate these big columnar structures? And it's outside what we call the tangent cylinder. So you consider the inner boundary, draw a cylinder, or just a line tangent to that. So if we were to rotate that around, we'd have a cylinder, and the rolls kind of manifest outside that cylinder, and then you can get more sort of amorphous, sort of turbulent convection in the polar regions. Unless you're very rapidly rotating, then you get roll-like structures there too, that they're a little bit different. Okay. That's a detail. But the most important thing to understand is that because the flow wants to be invariant in Z, and then you have this huge Coriolis effect anyway, you tend to get these big columnar structures that are aligned with the rotation axis and have this nice helicity to them that allows us to generate magnetic field efficiently. Okay. All right, so what I'll do now is just talk briefly about some of the magnetic fields in the solar system. So we talked about the Earth a little bit already. So the field strength is around a Gauss, and there's some tilting to the Earth, and we know that it's mostly dipolar, but it has some higher order spherical harmonics to it. Just kind of skip that. One of the interesting things you might ask, how do we know about the history of the Earth's magnetic field? And one way we know is through this interesting phenomenon called seafloor striping. Okay? And so the idea is that magma comes up into the seafloor, and then it's very hot, and then as it cools, the small scale dipole, whatever you call this, magnetic domains in the rock, right? The magnetic field of the rock tends to align with the Earth's magnetic field at that time when it cools. Okay. So as this magma comes up, it presses the rock that was previously generated out from this trench where it's erupting, and then that will also freeze with the magnetic field orientation of the Earth at that time, and this process repeats over and over and over. And so there are locations on the Earth, here's kind of a map showing one near Iceland, where you can see this striping of the magnetic field on the seafloor, and what you're effectively seeing is a history of the Earth's magnetic field. And so we know something about how it's flipping. Okay, and I think this is really neat when I learned about this. But it tends to flip every couple 100,000 years, but sometimes you have these very long periods of time where there's a stable magnetic field. Yes?
So as you move along the Earth's ridge,
Mm-hmm.
we already saw that there's not necessarily just purely a dipole field at any given time. So as you move along the ridge, depending on where you are, does this pattern change?
Yeah, it would change depending on the local field strength. Yeah, but it tends to give a pretty good sense, I think, of the orientation. It's one tool, right? It's looking at the magnetization of rocks that were effectively created at some time in the Earth's history. But yeah. One of the interesting things to note here, this little peculiar plot down here is just giving you a sense of how long the Earth was in one polarity versus the other. Okay, and so the reversals there are very irregular, and the length of time that the Earth maintains one polarity is also irregular. And so there are some of these huge lengths of times called supercrons where the Earth maintains just one polarity for a very long time, and then it starts alternating again in an irregular, chaotic fashion. Just a little diagram of the Earth's core. I suppose it's the radius of the inner core that's about 1,000 kilometers. The outer core is a bit more, about 2,000 kilometers in depth, so the full thing's around 3,000. What we think is that the core has two pieces, right? So if we go down from the Earth's crust, we run into the mantle. The mantle is convecting, but on a very, very, very long time scale, and it's actually not a conducting material, at least not in any appreciable sense. It's funny when you model mantle convection, you even drop out the inertial terms in the momentum equation. It's a very peculiar thing to model. Coriolis forces don't matter. It's basically just responding to what the temperature is doing. So there's just a very, very slow convection there. But then we have the Earth's core, and the Earth's core we think is divided into two parts. So there's a solid inner core, and then this liquid outer core. In fact, I think, does my next slide have this? I'll just mention it now. So the liquid outer core we think is mostly iron. It's iron with some light element attached, or possibly a couple of different light elements, but mostly iron. And over time, a couple of things are happening. That iron is sort of gradually freezing out onto the solid inner core. And also this light element plus iron combination is dissociating, and we're driving some form of compositional convection in the core too. So it's a combination of heat transport and probably some compositional convection. Just another turning slide on the mantle there. So yeah, the overturning time is amazing. It's crazy. It's a very slow process. Mantle convection is. Okay. And there's another estimate for the Rossby number of the sun. I guess it's due to the 500 years and the 365 days in the year. One of the interesting things you can do with the Earth, we can only observe the magnetic field at the surface of the Earth, but because we know that the mantle isn't conducting, we can say something about how the magnetic field must decay away from the Earth's core. There's nothing in the middle that's generating magnetic field that can kind of mask what's going on in the core. And so if you were to match on to an insulating layer, what you find is that the radial component of the field decays based on the spherical harmonic degree. And so if you're not familiar with spherical harmonics, you can think just like sines and cosines, but on a sphere as a first pass. And so this number here, L, is kind of like K in the sine and cosine. And so the higher L is, the more wiggly the spherical harmonics are, and the lower L is, the more bland they are. And so if you look at this, what does this tell you? So if you have a very wiggly spherical harmonic, L is very high. So if we have some really small scale features in the magnetic field, that will be encapsulated in the sense of having contributions from spherical harmonics of high L. But what happens to those? If L is very high, they actually decay away with height, right? And they decay away much more quickly than the low order components of the magnetic field. So what it means is that what we can do is look at what we see here at the surface on the crust and extrapolate back down. It's possible that some of the magnetic field has just decayed away past the point of us being able to observe it. Right? And so people do exercises like this quite a bit. They take what's observed at the surface, and then they back out what it must be at the boundary between the core and the mantle. Okay. And then this is what is used, this lower one. So CMB, by the way, is not cosmic microwave background. It's core mantle boundary. All right. So when you come from astrophysics and you start talking to the geophysicists, there's this immediate point of confusion. then you realize, oh yes, the Earth has some structure to it, and they're talking about that. So what's interesting, though, is this can be used then to, is one measure of the goodness of a dynamo model. Not the only one. In fact, it's very dangerous to use it as the only measure of goodness of a geodynamo model, and we'll get to that in just a little bit. This is just something I've already talked about. And then we'll move on to Venus. So this is kind of interesting. So you might ask, well, why? So Venus actually doesn't have a magnetic field, or it doesn't appear to be driving a dynamo. And the reason is that the heat is not able to escape, we think, from the core. And so there actually isn't any true convection because we're not cooling at the top. And the reason for that is that Venus doesn't seem to have any plate tectonics. Okay. So Mars, as far as we know, also doesn't have a dynamo. Does anybody know why? Oh, I hit the little animation a little too soon. This is just showing some measurements of very weak magnetic field on the surface of Mars. But we think Mars doesn't have an active core, right? So there is no fluid motion. There's no convection going on there. Mercury does actually have a pretty strong dynamo. Here's kind of a diagram showing it's kind of a poor diagram, sorry about this, showing the extent of its molten iron core relative to the planet. And so, for the Earth, the inner core is actually quite small relative to the size of the Earth. For Mercury, there's a pretty big region of molten metal to work with. Yeah? I do not know. That's a great question. Yeah, I am not sure. I am not sure. I don't even want to say I'm not sure if that's well understood. I am not sure. So, for the recording, the question was, why did Mars's core freeze out and the Earth's did not? Oh, we're still on Mars. I hit the wrong arrow. Some moons in the solar system have magnetic fields. Ganymede, for instance, has a appreciable magnetic field. Jupiter, I love this image from the Juno spacecraft. So a couple things here. First of all, Jupiter has a pretty big magnetic field. This is an image of taken near the pole of Jupiter. And what you're seeing here are not magnetic fields, but you're seeing flow patterns in the polar regions. And I hope that when you see this is somewhat reminiscent of what we were just looking at in terms of these columnar convective rolls. Now, how deeply these penetrate, there's still some question to that. Jupiter has an interesting structure, which I can show in just a second here, but I'll just say it now. Jupiter is very interesting in that most of it we think is convective, but then there's this thin stable layer near the surface. Surface isn't the word I'm looking for, but at the outer bounds of the atmosphere. And that is actually convectively stable. People call that like the cloud layer. You may hear it referred to that way. And so there's some question of whether or not these interesting patterns that we see on Jupiter are due to deep convective structures, or if there's just convection from below sort of pummeling that layer and generating turbulence, which is essentially 2D on a sphere in a rotating geometry. But this is very recent, right? This came out, I think, back in the spring. And so this certainly looks like these large columnar Busa rolls or banana cells that I was mentioning earlier. Jupiter has a pretty big dipole. I love this. I got the slide from Mark Nish, but I love that it's the archetypical Jovian planet. And then this shows a little bit of what we think the structure of Jupiter looks like. And so at the outermost reaches of the atmosphere, there's a layer of hydrogen and helium, which we don't think is convectively unstable. There's some question of what the core actually is, whether or not it's a rocky core or whether there's even an appreciable core at all is actually still up for debate. But then we have this layer, two layers. The most important things here are the big gray region and the big blue region. And so there's a layer where the conductivity is actually quite high. So it's a sort of mixture of hydrogen and some metals. And then we have this other layer, which is the molecular envelope. And there, the conductivity is not appreciable at all, so it's not a conducting fluid anymore. But all of this, we think, is probably convecting. One of the interesting things about Jupiter is that, you could say, okay, first of all, why do we even think it's convecting? So if it were just re-radiating the light that's incident on it from the sun, then we may not think that it's convecting at all. But it's actually radiating about twice of the energy that is incident on it from the sun. So there's some interior source of heat. And so we're not quite sure what's going on in the core there. But there's this big convecting region, but only part of it is conducting. Okay. And so this plot, yeah, go ahead. Oh, Mercury. I do not. I'm not sure why Mercury's core is so large. I will just say I'm more of a solar stellar guy, so I do apologize because I'm standing here as the the planetary person. But no, that would be some kind of a planetary formation sort of question. I would imagine that somebody has a sense of why Mercury has such a large molten core. So in Jupiter, this transition from a metallic to a molecular state occurs pretty far out, but there's still an appreciable region where there's convection. And so what we think is that probably the dynamo is operating from maybe 80 or 90% of the way in, but that convection is actually taking place over a much larger region of the star. And so this is interesting from the standpoint of modeling and trying to understand what the dynamo might actually look like. This just shows kind of a magnetic field mapping of Jupiter before Juno, so it looks a lot like what I showed on the first slide. And then with Juno, which is orbiting Jupiter multiple times and taking measurements of the magnetic field, we're starting to get some higher resolution views of the magnetic field there. Saturn is interesting. That Saturn has a substantial magnetic field, so it's around a Gauss. What's interesting about Saturn's field is that it's nearly aligned with the polar axis and it's axisymmetric. And so why might that be a puzzle? Just kind of curious, does anybody heard something? That's right. So from Calling's theorem, right, we know if you have a purely axisymmetric flow, we cannot generate or sustain a dynamo. And there's kind of a corollary to that, which says that because of Calling's theorem, you cannot get an axisymmetric magnetic field. And so there's a lot of open questions about how this is sustained, what's going on beneath the surface in Saturn, what does the differential rotation look like that it drives. And then just really quickly, I'll just mention, Uranus and Neptune, also magnetic, kind of like I talked about before. So the thing, though, about planetary dynamos, we can observe their magnetic fields, and then we have some notion of the structure of these objects, but we aren't really able yet to seismically sound the planets, except I believe there's a mission going to Mars that's going to do this soon. Does anyone know about this? I feel like this is about to happen with Mars. There's going to be a little probe that lands and does some seismic analysis. But so we're actually quite limited in terms of what we know about the interiors of planets, much more so than Earth and the Sun. And so as we try to understand how planets generate their magnetic fields, we tend to rely heavily on models, right? And so what we would do is we would solve the MHD equations in a rotating frame. I won't put them up here. We usually work either, it depends what we're doing. If we're doing a gas giant, we work in what's called the anelastic approximation. So if you're familiar with the Boussinesq approximation, it's very similar, except it emits a background variation in things like density and pressure and temperature. Otherwise, if you're working in something like the Earth's core, there's actually not a lot of variation of density across the Earth's core. Density varies by something like 0.6 scale heights across the core, so it's very weak. It's not even an E-folding in density across the core of the Earth. So we tend to work either in a fully incompressible approximation or a compressible approximation that lets us retain the density variation. And then, depending on the object you're looking at, you may heat from below and cool from above, or you may have some distributed source of heating throughout the layer. This is pretty typical for the gas giants. It's typical for the sun, for the rocky cores or the molten metal cores. You'll just kind of heat from below and cool from above, like we talked about earlier. So what is the danger, though, in simulations? You have to be very careful about how you interpret what comes out of these things. I am a modeler, so I'm a big fan of simulations. But you have to be extremely careful when you interpret those results. And if you just look at some of the non-dimensional numbers here, so if we look at, say, the Rayleigh and the Ekman number for the Earth, we get some huge values for the Rayleigh number and very small values for the Ekman number. But then if we were to compare that to what we can actually achieve in simulations, we're orders of magnitude away, okay? And so the efficiency of convection that we can achieve in our simulations is nothing at all like the efficiency that's actually achieved in a planetary interior, at least based off of the numbers that we know concerning the object. The Reynolds numbers, the funny thing for the Earth, at least, is that the magnetic Reynolds number is, and Reynolds number is not on there, is getting approachable, though not so much so for Jupiter, right? We can get, in simulations, we can get a Reynolds number of about, or a magnetic Reynolds number of, still, Reynolds number, same thing though, about 1,000. Okay? And if you ever wonder what that means in terms of modeling, the Reynolds number is basically telling you how many grid points you need in each direction. It's they're very closely tied together. So people can run models now that are like 1,000 cubed to 4,000 cubed, right? Somewhere in that range. So you can get Reynolds numbers that are order 1,000. It's even worse for the sun. I threw this up yesterday, but now we've talked about Rayleigh numbers, right? So Rayleigh numbers I didn't mention. In fact, was it on the last slide? So yeah, models, 10 to the 6, 10 to the 7. You can probably push 10 to the 8 now if you try. Of course, for the sun, the Rayleigh number is like 10 to the 22 to 10 to the 24. Reynolds numbers are huge for the sun, right? So if I wanted to really fully capture all of the length scales in the solar convection zone, I would need 10 to the 12 points in each direction in my domain, right? This is just impossible to do. Nevertheless, we can kind of push out into these extreme parameter regimes, and we find that even as we push into more turbulent parameter regimes, these basic balances still tend to hold. Taylor-Proudman still exists even in a very turbulent high Rayleigh number flow. We tend to get very columnar structures. This is a geodynamo simulation from Akira Kageyama. And eventually, these structures, for reasons I'm not going to get into, can actually form these very thin filamentary vortex sheets. But the thinness of these things is still related in some sense to the Ekman number and to the rolls that initially manifest. And actually, I should say that was hydro. But then if you're in MHD, it's still the same thing. You still tend to get these interesting roll-like structures, and they have alignment with the rotation axis. From these sorts of thought experiments where we run these big different dynamo models, one of the things that's come out of this is that as you're rotating more rapidly, or as the Coriolis force becomes more important relative to inertia and buoyant driving, say, we find that dynamos tend to become much more dipolar in nature. That's a pretty robust result. The other thing, I'm not going to get into this right now due to time. What you can show, though, is that also the ratio of the magnetic energy to the kinetic energy. Oh, am I out of time? Oh, a break. I'm sorry. I'm so sorry. Yes, a break. I will pause. Yes, no, absolutely. Yeah, I thought that was just normal for when I I spoke. Oh, thanks. Sorry about
I
that.
really liked examples.
Oh, thanks.
Very neat.
Oh, thank you. And I'm glad. So, oh, I guess I'm
You've
on.
been making them solve differential equations.
Yes. At 9 in the morning. Bit more coffee. Sorry. Hi. Hi.
Discovered one number I've been using in class that's probably not right, where I picked it up.
Which one?
Taking the overturning for the
give people just another minute. I actually don't have that much more. So. So I'll give these people just one more minute. I don't know if I should wait on them or they just had enough. Time is it? Oh, 47 minutes, good. It's probably mine from yesterday. Let's take these two. Let's see. Oops, go ahead. Oh, thanks. Post, recycle. Actually, I was going to skip the exercise, but I do want to mention this point. When you're in a rapidly rotating MHD system, a lot of times the balance that you strike is what's known as magnetogeostrophic balance. Or sometimes it's referred to as MAC, which is like magnetic, Archimedes, so buoyancy, and Coriolis balance. But the idea is that the fundamental balance that's struck is between the Lorentz forces and the Coriolis and the pressure and the buoyancy forces. Okay? And then when you consider this balance, you can ask yourself, okay, what might be the ratio of magnetic to kinetic energy that I get out? You can kind of work through this yourself. But what you find is that the magnetic versus kinetic energy should grow as the Rossby number becomes smaller, okay? Which is kind of interesting. What you're really doing is you're tapping into the energy associated with the rotation of the system itself. And this is borne out by a number of different dynamo models. These were all run, I'm fairly certain that all of these, there may be some small exception in there, but these were run just in a simple Earth-like geometry, and different Rayleigh numbers and different Ekman numbers. And here we're just kind of seeing that basically well, there's this peculiar axis down here, but basically this notion that magnetic energy grows as rotation rate increases is borne out through models. I won't say too much more about that. People do a lot of this sort of thing, though, I should mention. When you get into convection theory and convection modeling, whether that's MHD, convection, or not, a lot of times what we're interested in is how do our outputs scale with our input parameters. So how does the kinetic energy scale with Rayleigh number? How does the heat transport efficiency scale with Rayleigh number? And so these sorts of scaling laws are looked for quite a bit of the time. One of the nice things about them is that you can use these sorts of scaling laws to assess where you are in parameter space, and then based on kind of the slope, sometimes this tells you things like whether or not diffusion plays a leading order role in your model or not. Right? This is the ultimate problem with all of our models. This is why our non-dimensional parameters are so far off, is that we cannot simulate something with the actual diffusive values associated with the object that we're interested in. But we can make statements about whether or not diffusion is important to leading order or not. And so I would say that's kind of the state of the art right now. Can we get to a regime where we can quantifiably state that, yeah, diffusion is not in the leading order force balance. For instance, there's no diffusive term that appears here. So if we observe a scaling that comes out from this sort of, that is predicted by this sort of force balance, we can make statements about the relative importance of diffusion. Okay. If a modeler doesn't do that, just tries to show you a result that matches, you should be very suspect of that result. Okay? Anyone who doesn't tell you in some fashion, even if it's just a quick statement, something about how important diffusion is in their model, it's not necessarily that they're being dishonest, they just may not appreciate what problem they're actually solving. Okay? So always be suspect if you're not told in some fashion, preferably with a scaling plot where they demonstrate a transition between a diffusion-dominated regime and then a diffusion subdominant regime. Just be a little suspect. So why is that important? So what's interesting here, this is showing the inferred magnetic field at the core mantle boundary of the Earth in the upper left, and then 3 different models. And so if you ask yourself, which of these models best matches the core mantle boundary as we believe it to be, which one would you say? I mean, I think it's... Someone say it louder? B. Yeah. So it actually turns out that B's parameters, even though it matches very well, its non-dimensional parameters are much further away from the Earth than C or D. So it's kind of interesting. So B is in effect the worst model if you were to start out a priori, just saying I'm going to dial in these non-dimensional numbers. And C and D are far superior. And in fact, the fact that we get a match is a bit of a coincidence. And it, who knows if it's telling us anything useful or not. But we may not want to use that model to make predictions. And I'll just kind of... So this is sort of the thing that you always have to worry about with modeling. Are you getting the right answer for the wrong reasons? Here's kind of another example of this. This is some work done by Krista Soderlund, who's at University of Texas at Austin now. And she's showing her simulation here where we see the radial magnetic field on the core mantle boundary, and we see structures of similar spatial extent to what we see with observations. Okay, so observations are on the left, some paper by Andy Jackson from a few years ago. And so that looks good, right? So what is the problem, though? If you were to look inside this model, you would see flow structures that look like this. In this case, we're showing the Z component of the vorticity, so you're seeing some measure of how spirally things are. But it turns out just to be really nice to illustrate the convective structures that are achieved. So what is the problem here? The problem is that we know that these structures, spatial extent depends on the Ekman number. Okay. And so there's some columns kind of like that. I believe the Ekman number here, yeah, is 10 to the minus 4. Okay. Of course, in the Earth, it's much smaller. It's like 10 to the minus 15. And so even if I drew this little red line here, that would be about 1,000 times too wide. Okay? So we know that even though it matches really well, and I should say Krista shows this slide, as does her former PhD advisor. In fact, that's where I got it from, so I'm not criticizing anybody's model here. This is true of many models. Even though it matches quite well, the underlying physics are just really far off. And it's not just that the non-dimensional numbers are far off. The structure of the flow itself it's highly unlikely that it looks like that, Now you might ask the question, is it possible that somehow these small-scale structures coalesce into larger-scale structures? We're in a very rapidly rotating system when we consider the interior of the Earth, so it's 2D in some respects, and so maybe there's some kind of inverse cascade going on where small-scale structures merge into larger structures. It's a possibility, but we can't say that from this sort of model. The other question is, once we're in this parameter regime, so I'm trying to remember the actual spatial scale here. I believe maybe it's like a kilometer is what the red line would be in the actual Earth. And so do we expect any structure to hold that's a kilometer in size to hold its coherence across the full diameter of the Earth's core? Is that even possible, right? And so this is really one of the big problems right now, is that we know in the geodynamo, and we know in the solar dynamo, we know in all of these systems that we don't really have the flow structures that we know must be there, or we know we're not even approaching what must be there. There are some ways to get around this. For instance, we have these approximations we work in, the Boussinesq approximation, which is interesting. So we assume the flow is incompressible. One nice thing about that, it filters out sound waves. In the inelastic approximation, we get the same thing, so we don't have to worry about sound waves, but we can retain density stratification. Both of those are based on small perturbations about some otherwise constant thermodynamic background state. You can do a similar exercise with rapidly rotating fluids. And so what I'm showing here are just some simulations that came out of Keith Julian's group at CU. And what they do is they work in a limit where the Rossby number is vanishingly small. So it's an asymptotic limit where your Rossby number is approaching 0. And they look at convection in these sorts of regimes. And they still can't get down to the spatial scales that we're really interested in. All they can do, they can kind of model what might be like the polar region in the Earth. So it's in a box. But what is interesting is these small-scale structures. So it's very turbulent, and what you see here is actually very rotationally constrained, even though it's occurring on a very small scale. And they do merge into these larger-scale vortices. And so there's really some open questions about what does the flow look like inside the interior of a planet, whether that's the Earth or a giant planet, or frankly inside the Sun. Because we probably have things occurring on a variety of scales, and there's exchange of energy between these different scales. And how that exchange happens is going to depend quite a bit on how rotationally constrained the flow is, how turbulent the flow is, how strongly it's driven. You can look at the summary slide when the slides are online. One thing I did want to kind of close with really quickly, I had this nice image of Juno, and so I will show one model that I like to show. This is some work done by Maritz Heimpel, who's at the University of Alberta in Canada. What you're seeing here is the radial component of vorticity in a Jupiter model, and it's a little unfortunate since this isn't an HD projector, but resolution is pretty good. What happens here is that you're able to see the vortices this way very well, and there's a transition kind of from the pole to the equatorial regions. So the equatorial regions actually have a very a banded differential rotation structure. Let me kind of play that again. Oops. But the radial, here you have these columnar rolls, and so the vorticity is directed that way, and so it's not aligned with the radial. So some of this weirdness you see is just a geometric effect, because we're looking at radial vorticity, not z vorticity. But you see that so first of all, the time scale you see here is actually rotation periods. Okay, so this thing is just rotating away, tick, 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 tick. But if you look at the polar regions, the flow is actually evolving very slowly, right? So we have these very long-lived coherent structures, and they merge together to form other structures, then they cleave and separate. So it's this is actually I should say, kind of a state of the art right here. This was done on the Mira supercomputer. So I worked with Moritz a little bit on this, and he used 500,000 cores at a time on this computer, and I don't even know how many days he ran for. I mean, we burned like in total we burned about 900 million core hours over 3 years, and this was something like 400 or 500 of that. So it's a very, very expensive calculation to carry out. But here we have a rapidly rotating system in very, very small scale flows, and so this shows you one illustration of what that might look like. But even here, his ECMA number, I forget, it's maybe like 10 to the minus 5 or something. It's still maybe 10 to the minus 6. It's still very, very far from Earth-like, or this is meant to be a Jupiter model, Jupiter parameter regimes. So I'll just close there. Thank you all for your attention. One thing I'll mention really quickly, I have to run to the airport in about 10 minutes. I'll be back for the lab, so if you have questions longer than 10 minutes, I'm happy to chat later this afternoon. So, great. Thank you. Any questions? I do have 10 minutes. Yes?
So, along with the limb of the pole, it's almost there, like,
Oh, yeah, this is the way some of us render these things. This is actually a 2D spherical surface output by the simulation. And then we give it a little bump mapping based on the value of the vorticity. So where it's, in this case, where it's negative, he's made the surface extended a little bit. And where it's positive, we depress it. So this is a kind of just a visualization technique that gives you some sense of the 3D structure of the flow from a 2D map. Notice there's like some lighting on here too, so it looks very 3D. Yes? No, though this is a new computer, so I don't have the slides on here. No, what is interesting though about this model is that if you were to look at this in terms of just the zonal flow fields, the longitudinal flows, you actually get quite a bit of banding. Where the red spot comes from is not so clear, but you have quite a bit of shear associated with the bands on Jupiter, and so probably it's generated through some sort of turbulent shear effect. But as far as I know, no one has been able to regenerate that in a model or not. But otherwise, if you were to look at this in kind of a different light, it would actually look remarkably like Jupiter. It's a pretty impressive simulation he's done here. Oh, but one thing I'll mention, it has he's only modeling the molecular envelope. So there's no MHD in this, and the deep part of Jupiter, the actual conducting layer, is just left out completely. So this was really an approach to a Jupiter model, and then I think we started to get some interesting results, so pursued for a bit longer than maybe we had planned. Other questions? All right. Well, thank you. I guess I'll say.
Any predictions on when they'll